Hello wonderful person, this is Anton, and today we're going to be discussing a somewhat mind-blowing discovery coming from the center of the galaxy. And in this case, a discovery, and technically a somewhat thorough analysis, of a very unusual extreme star. A star that's located extremely close to the central black hole, and that's actually experiencing effects we've never seen any other star to experience because of its proximity to the central black hole. And though, as you see from this time-lapse, for decades now, we've actually been watching these stars dance around the central black hole Sagittarius A star, with some of these stars even being used as a kind of a test probe to see if Einstein was actually correct about his general relativity. Today, we're going to discuss this recent study from July of 2026 that's now revealed a star that basically breaks all previous records and that seems to experience effects that are truly mind-blowing. A star referred to as S301 that seems to reach velocities that are the highest in the entire galaxy, with this star moving much faster and passing much closer to the central black hole than almost anything we've ever seen ever. But in this case, this discovery is not just about finding the fastest star in the galaxy, it's also about finally measuring something that we've never actually been able to prove our galactic black hole to possess. In this case, the black hole spin. And so in this video, let's discuss the study and exactly what we know about this star, and discuss the implications for astronomy. But first, let's actually talk about these types of stars in general, because there seems to be way more than one in this region. And well, technically they're referred to as S-stars. Stars orbiting the central black hole, whose bizarre motion allowed scientists to pinpoint exactly where the black hole was. And for many years, the gold standard was the star referred to as S2, a star that orbits the central black hole every 16 years, and was officially used to prove that space-time indeed seems to be warped in a very bizarre way in these regions, and was basically curved exactly as Einstein predicted. So essentially here, this was one of the first such confirmations using the central black hole. But this new discovery, S301, is a little bit different. First of all, this is a faint main sequence star that's technically very similar to our Sun, but just a little bit more massive. But it also seems to have the shortest period around the black hole, taking approximately 8.7 years per orbit. And so this seems to be the fastest moving object in this region. But it also has an extreme orbit. It essentially resembles something like this. It's extremely eccentric or extremely stretched, with the total eccentricity of 0.98. So it basically is shaped like a very long, thin needle. And so it actually moves pretty far away from the black hole just to come back and pass extremely close to it at extremely fast velocities. And at the closest approach, it's approximately 136 Schwarzschild radii away from the black hole, or the distance equivalent to the distance of Uranus away from the Sun. Although in this case, because this black hole is pretty large, technically its outer edge would be in the same position where we find Mercury. But the point is that the star comes extremely close to the event horizon, and at this point it's moving very, very fast, approximately 25,000 kilometers per second, or approximately 8% of the speed of light. And that's actually what makes this particular star so unique and so unusual. It's basically the only object we know of so far that seems to experience such a ridiculous relativistic effect by traveling so close to the black hole every 9 years. And well, because of this, there are a lot of things we can learn about the system and the black hole by observing how the orbit of the star changes with time. For example, we know that in physics, when it comes to black holes, they really only contain 3 specific properties: mass, charge, and spin. And we already know the mass of the black hole, approximately 4.3 million solar masses, but its spin has remained elusive, even though we actually have the image of the black hole taken by the Event Horizon Telescope. But any black hole that has a spin basically ends up dragging the space-time along with it, creating what's known as the length-theory precession. Something that, once again, this video from David Butler explains pretty well visually. You can find this video in the description. And so basically here, as the black hole spins around, it also drags space-time itself along with it, which causes a lot of things around the black hole to change over time. And that of course includes orbits. And while previous observations of the S2 star were pretty good for measuring the overall curvature around the black hole, it was just a little bit too far away to feel the actual twist caused by the spin. But this star is not. This one is at least 10 times closer to the black hole, and so it's actually a lot more sensitive to this twisting of space-time, allowing scientists for the first time in history to have an actual practical way of measuring this by looking at the stellar motion and the changes of orbit of this particular star. And so what exactly was done here, and how exactly was this measured? Well, in order to see all of this, researchers had to rely on the Very Large Telescope in Chile, and specifically the gravity instrument, which actually allowed astronomers to track the star's position across 19 different datasets for approximately 8 years. And one of the most exciting discoveries here was the orbital precession. Okay, let me quickly explain exactly what this is and why this is important. So, according to Newton's laws of physics, a typical star should follow a perfect ellipse and basically return to the exactly same spot every single orbit. But in the late 19th century and early 20th century, astronomers realized that for some reason, the orbit of Mercury was always not exactly where it was supposed to be. Now this is a little bit exaggerated, but basically, with every passage, it would always shift by just a little bit. And the only way to explain this using Newtonian laws was by basically having some other object somewhere extremely close to the orbit of Mercury, possibly even extremely close to the Sun. And so here this tiny shift, which is actually super small, a tiny fraction of a degree every century, eventually led to the proposition of a hypothetical planet extremely close to the Sun. Back then, it was named Vulcan. But despite multiple searches, there seemed to be no Vulcan anywhere. And so by early 20th century, astronomers were basically scratching their heads. They could not figure out what's happening and how to explain this until this guy. This guy explained it. His new general relativity explained everything extremely well without any hypothetical planets. And it explained it by having a massive object like the Sun twisting space-time with it, creating these effects. And so this was actually one of the first official triumphs of the general relativity. Since then, quite a few similar objects and similar phenomena have been explained in the same way. But in contrast to Mercury, the star S301 shifts way more. As a matter of fact, it shifts so much that we can physically see it in a telescope after every single orbit. With this recent data confirming that the star is moving exactly how it was officially predicted by general relativity. But as we watch it over the next decade, this extra shift caused by the black hole spin should become visible. And so in this case, astronomers predict that by 2035, we should have enough measurements and enough data to figure out the exact black hole spin. At the moment though, with just 19 measurements, the spin is currently still unknown. But from what we see, the closest approach to the black hole seems to advance by approximately 2 degrees every single orbit, which is definitely the highest precession we've seen from any object. But on top of this discovery also tells us just a little bit more about the galactic center, and also potentially solves the mystery of where some of these stars came from. Because even today, it's a little bit difficult to explain their origin. Mostly because we know that stars should not be forming so close to the black hole, and technically a lot of these stars should have already been destroyed a long time ago. But because of this extremely high eccentricity, here we can certainly state that this star arrived from somewhere else, and was very likely stuck in this orbit because of the mechanism known as the Hill's mechanism, which is kind of explained in this image. You essentially have some kind of a binary star system, where 2 stars orbiting each other accidentally wander too close to the central black hole. And while one of the stars unfortunately falls into the black hole and gets ripped apart. But the second star survives by either being kicked out of the galaxy at ridiculously high speeds, basically becoming what's known as the hypervelocity star, the concept you can learn about in one of the videos in the description, or, as in this case, can actually get stuck in its current tight orbit with extremely high eccentricity and approaching the black hole very close every single orbit, which essentially suggests that this particular star seems to be a kind of a pristine fossil of a capture event that most likely happened a few million years ago. And it also suggests that there could be hundreds of other faint low-mass stars in a very similar orbit, moving even closer to the black hole. But we just haven't discovered them yet because they seem to be much dimmer and are thus much more difficult to detect. As a matter of fact, it took many decades to discover this particular star that's technically even brighter than the Sun. So it would not be unusual to have much dimmer stars similar to red dwarfs. But by studying this object, we're actually doing much more than just verifying Einsteinian math, because here we're also testing the limits of modern physics in a kind of a strong gravitational field environment. Especially because the ideas from general relativity do work pretty well and explain things quite beautifully when it comes to massive objects, but do not work so well with much smaller things and with quantum mechanics. And so in this case, this potentially might take us a little bit closer to various alternative explanations such as quantum gravity, and might provide enough evidence to either prove or disprove these ideas in the future, especially because certain theories even suggest that near supermassive black holes, gravity might even behave slightly differently compared to what Einstein predicted. And so in this case, by studying these stars, we'll actually be able to collect all of the necessary data to test all of these ideas in modern physics. But as of 2026, after observing these stars for several decades, right now they do seem to suggest that current models are correct, and various mathematical descriptions of black holes, such as the famous Kerr metric, seem to be pretty correct in describing the black holes and the universe in general. So based on these observations, we seem to have all of the right facts about black holes, the lens theory in precession, and all of the relevant effects on the space-time itself. But because this is such an exciting discovery, it will definitely be teaching us so much more about modern physics than any other object in the galaxy. And so even though the universe is governed by these giant invisible monsters like Sagittarius A star, it's really the individual stars that still tell us the entire story. But until we learn something else, that's all I wanted to mention. Thank you for watching, subscribe, come back tomorrow to learn something else. Support the channel on Patreon where you can find additional videos without any ads, and can DM me directly, or by joining a channel membership that grants you early access and a few more things. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.